All right. Good evening, everyone. Welcome. Thank you for coming. I think we have a lot of people. We have 36 people online. I think it's great. A couple of technical things. So these are people who will present today. We will change the order. Walmart will go first, ClickHouse second, and LinkedIn will be third. So these are the times when the presentation is about 30 minutes and 5-10 minutes for questions at the end. We will monitor the channel. If there are questions on the channel, we will read them aloud. Everything will be recorded and later posted to YouTube under LinkedIn Engineering. If you have any questions in the room, just raise your hand. I'll give you a mic. If you have any any questions online, click the Q&A button. We will be monitoring it. Again, if you want to do a presentation at some other time, feel free to reach out to any of these people on the meetup, and we'll try to set it up for you for the next time. We're doing this every 3 months, so the next will be somewhere in April, I guess. Next meetup. All right, any questions so far? No? All right. Then you guys come here. Let me stop sharing. You can share. Let me quickly introduce the speakers. So right now we'll be talking. These are our guests from Walmart. You're Ravi, right? Ravi Mate is software engineering director, experienced in large-scale system design and senior team mentorship. Technologies, everything under the sun, including distributed databases. All right.
Hello. Yeah. All right. Thank you, LinkedIn, for hosting this. This is pretty neat. Thank you. A lot of preparation work goes behind it. Appreciate it for hosting. I'm with a group of two leads from the messaging and streaming platform. I'll talk about a little bit about what the Walmart Global Tech Platform is. And what kind of problems we were seeing from the messaging and streaming platform. And we'll talk about some solutions that we designed, and we did some blog post about it. And some that we are developing under development, what problems we are yet to solve and all that. We will talk about that. I'm assuming many of you might know what is Walmart. Most of you might have shopped at Walmart. In the store, and if you haven't, try the walmart.com. It is much faster in terms of delivery, in terms of how fast you can get the groceries or the express orders delivered at your home. And majority of that pipeline is powered by the Kafka internally. I'll give you some quick stats. Within, even though when we say Walmart, within Walmart there are multiple business units: Sam's Club, Walmart International, Walmart Canada. Bunch of those business units runs as a independent services solving the business use cases. They all uses this global tech platform services, which we are responsible in terms of providing the platform for the different business units. There are around 10,000 plus business units across the globe, across 19 countries. Interesting fact is within US, we can deliver stuff in a day for 90% of US population. The last part is a bit interesting. Especially when we are evolving from stores to the e-commerce side. One of the great advantage Walmart has is it has a footprint, stores across the US. we would like to leverage those stores to do the delivery faster. That's why I'm saying, like, in reality, if you go to walmart.com and order stuff, it is much, much faster than any other competitors. So what over last few years, we started using Walmart stores as a last mile delivery hub. What that means is there are systems that are helping the stores. There are systems at the e-commerce side. Lot of integration between the services happened over the last decade. And they all done through some messaging platform, either Kafka, AMQ, or IBM MQ, some of those different messaging platform, but majority of that is in the Kafka area. I'll just quickly go over how the Kafka evolved or adapted within the Walmart. We started a long time back with the 0.8 version. We still operate some 0.10 version. I don't know if anyone has that experience of going through the really older version. Sorry, I think, but we still operate some of them. A majority of our 1500 plus Kafka clusters runs on 3x version. We just recently rolled out 4x version for some new clusters. There are around 100K plus topics, 25,000 plus application integration that happens internally. Some raw data, like the traffic at the producer side and the consumer side. But the other interesting fact is we have this triplet model infrastructure deployment, where all our workloads are deployed on at least 3 cloud providers. Obviously not AWS. One we have with the private cloud. They are typically all our systems run in this triplet model. When we are operating this 1500 plus Kafka clusters or other distributed system within the cloud and data platform, we leverage a orchestration platform called OneOps. It's an open source one, oneops.com, which Walmart open sourced it a while back. It's a pre-K8 world, but it works very well for the VM-based orchestration layer. And that's kind of powering a lot of stateful systems within the Walmart. And I'll quickly talk about what challenges we went through when we are over the last quarter. Obviously, when I started with Walmart in 2013, there are like few hundred, not like in a 2-digit cluster, very few topics, very few, like it's some of them are managed by the application teams itself. It's not even like a very platform specific. Lot of things we just adapted, like leveraged it, like start owning the application infrastructure and start building the platform from there. And we saw growth, tremendous growth over the last few years. But the growth part is very easy. We built pretty good control planes and all that worked out very well. But the problems that we were not able to solve is when the applications start using it. There are a bunch of consumer rebalancing issues that sometimes resulted in missing the business SLAs, missing the delivery timelines, a bunch of those things. And we were trying to solve that problem with some best practices guides, tuning the parameters, hey, change this poll records or session timeout this way, and multiple different ways. But we couldn't scale because of the number of problems and the way that we were trying to solve. And within these pipelines, after the orders get placed, there are multiple systems that get involved, and they are all orchestrated through Kafka pipelines. There is always, once in a while, some consumer don't understand the message format or don't like it. There is a poison pill messages. Handling some of those is like a bit more. Not everyone implements the best practice consumer code. Not everyone writes the best best code to handle all the error scenarios. And within these multiple business areas, everyone tried to solve that problems by building some frameworks. And we ended up having 10 plus Kafka client frameworks, and we're running with around 50 plus running on different Kafka versions when we did a quick audit of the whole system. That kind of became like our main pain point. Then we tried to we went around the industry and tried to compare what options are there to solve this problem. Then finally we decided there is something for we need to build something ground up to make this possible. That is when we developed a platform called messaging platform service. To talk about a bit more, invite Bali. He's our architect, who kind of envisioned the MPS and then build it, developed it, and we put a blog post about it. Over to you.
Yeah. Thank you, Ravi. Yeah, hey everybody. Yeah, so Ravi mentioned the scale of Walmart, where we were processing 1 trillion messages every day. And with that scale, all the standard problems that comes with Kafka translate to partial failures or critical failures within our system, as we have orchestrated a variety of services that talk asynchronously over Kafka. So that results in latency spikes, missed SLAs, operational toil. So we wanted to solve this problem, and then we were just rethinking the relationship between a consumer and a partition. And we solved this problem by rethinking this and presenting a managed service. We call it messaging proxy service. So what was breaking for us? First, as Ravi mentioned, a lot of rebalances. Applications were using Kafka clients directly in their code. Any large garbage collections, stop of the world cycles, downstream dependencies, databases getting slower, the processing not happening faster. So that results in rebalances. And now they start falling behind because they are accumulating a lot of lag. To process that lag, they're going to auto scale. They're going to add more machines to that. And that again results into another rebalance. So we sort of fighting with the protocol here now. Like, to do something, you do something else, that again gets into the same trouble. And the second bucket of problem was deep coupling of parallelism with partitions on Kafka. So we have our cycles of services where they see a large trend of messages through some seasonal cycle. Sometimes they are low. And to handle that seasonality, we keep them at a number of partitions that are peak of peaks. So imagine scaling your system throughout 365 days to handle the peak that might happen a couple of weeks, a couple of months. So that's where we saw cost optimization potential. And on top of that, we wanted to provide extra features like automated DLQs, DLQ associated with the topic, so that we can take the poison pills out of the message stream, put it on a DLQ to be analyzed later. Message filtering that can be done at a proxy layer. So this is high-level architecture for our MPS. So first problem we wanted to solve was rebalancing. So that's where we separated our proxy layer into two different thread groups. One is a reader thread that pulls some messages from Kafka, put it into the pending queue. So that reader thread has nothing much to do, pulling the messages, putting into the pending queue. So it's not gonna cause any rebalance because it's not waiting for anything else. And we have a writer thread that's responsible for taking the message and publishing to the services who have exposed their APIs through REST, HTTP REST, and now they are not hosting any Kafka client libraries in them. So what it enables us is zero rebalances. Some rebalances may happen if your pod crashes for some reason. But throughout the service, we have seen a lot of stability because we have decoupled the consumption of a message from the processing. And the writer threads, they take the message from the pending queue and publish to the service. And now we have decoupled services from the consumption on Kafka. We have this proxy layer. The services can scale as much as possible. And if we see a lag, we see a lot of orders coming for in a certain days, they can scale independently. And now we are scaling our Kafka partitions for the throughput, but not for consumption parallelism, because we can handle that consumption parallelism on our end by massively parallelizing across multiple service pods. And second thing we got done there is key level ordering. So all the keyed messages go over the Kafka partitions, and we don't want to be bounded by the parallelism that's proportional to number of partitions on Kafka. So here we implemented the logic where when we are reading the batches of messaging into the pending queue, we can separate them by their key. And we can parallelize our consumption of messages at every key level, every key. So assume like having a key A coming into the system. So there could be multiple updates on that key, and you can assume that key to be an order ID. So there could be multiple updates on the order coming. And we keep a map, a soft state within our system that tells us what is in flight. Is there an in-flight message for a key? And if there is an in-flight message for a key, we keep that message aside and we can move to the next one, but not committing the offset. So as the messages are getting processed, we are getting a successful HTTP responses or failures. And on failures, we can do retries, exponential retries with a bound, and then we can auto DLQ them. But at any time, we'll keep accumulating the responses coming, and our offset committer actually sees like what are the messages I have offsets I have seen on a partition, and then it starts to commit those offsets in a sequential order of offsets. Otherwise, it will keep the state until the message has really been processed and acknowledged by the service. This is all soft state in the memory, and we have seen very less rebalances because now we have a few nodes who can consume and send data for processing to other services. So this eventually becomes IO bounded system. It has no CPU processing to be done. So thus, we gain the stability with that, reducing all the rebalances we have seen earlier. Now we got the true elastic services. Now the services can scale at an independent scale. They are totally independent of how many partitions they have on Kafka. And we got some cost benefits too. Now we are scaling our Kafka partitions for throughput rather than all the max parallelism, and we can keep our Kafka resources to a level we want. Yeah, but we still didn't solve all the problems with MPS. We still have partition lag skewness, like the keyed messages. Some partitions may become very heavily loaded, and we still have some bounds, like how many messages will pull into the in-memory. That skewness sometimes cause some message delays, and a partition level quality of service. So within a topic, we have a mechanism where we can do priority bucketing based on the partition ranges. And if we want to maintain quality of service on the consumption of those partitions, we couldn't do that earlier. But then we enhanced our product to get new features which actually solve those challenges. And I'll invite Raghu to talk more through about those challenges and how we solved it.
Thank you, Bali. Hi, everyone. My name is Raghu. Yeah, so as Bali mentioned, so most of the problems we have solved using the messaging proxy service. But when we are operating messaging proxy service at a large scale, like we have, as Ravi mentioned, 25,000 integrations, right? So we started seeing these issues. So the lag skewness and partition level QoS. So I will cover more in the next slide. So to solve those issues, we created a new partition assigners. So the first one is a lag-based partition assigner. So let me share some context. So Kafka has a pretty solid Kafka assigners. So for example, a round robin assigner, range assigner, and sticky assigners. And Kafka assumes that the traffic across those partitions are even, and just distributing these partitions among the consumers means distributing the load. But in real world scenarios, it works a little bit different. So in all the partitions, they may not get the same throughput because of various reasons. So because of the throughput patterns, or uneven producers, or maybe the choice of the message keys. So for example, if user is selecting a zip code as a message key, or maybe a store as a message key, then definitely one store might have more throughput compared to other stores. So that creates a skewness in the throughput, skewness in the lag. So few or some of the partitions lag far behind the other partitions. So let me take one concrete example here. So we have a 9 partition topic where we are consuming from 3 consumers. So consider that one of the consumer is slow because maybe it is running at high resource utilization, or maybe the downstream system is not working well, or maybe it received the poison pill message. It could be any reason. This consumer is slow. So because of that, the lags started piling up on these 3 partitions. So let's say maybe it cumulatively we have 1 million lag here, and it takes 30 minutes to process this whole lag. And this single consumer needs to process all these partitions lag, while the other consumers are just sitting idle. So to solve this problem, to distribute the load equally among the consumers, we created the lag-based partition assigner. So the goal is just find out all the high lag partitions and just distribute them among the available consumers. So that's our goal. So we by using the lag-based assigners, we were able to do that. And then if you compare the left hand side and right hand side, right? So in the first case, only single consumer is processing that complete load. But now in the second case, we were able to distribute all these high lag partitions equally among the available consumers. Okay, so this is the pseudo code for our lag-based assigners. So what we are doing is first, we are getting all the partition information, if of a consumer group, and then we are calculating the lag by fetching its partition end offset and committed offsets, and then using this we are calculating the lag, and then we are sorting the partitions by their lag, so that we can distribute these sorted partitions using our default assigner. So in our the current example, or in our use case, we are using the sorting algorithm. Just we are sorting the partitions based on the lag, right? So this is working well for us, pretty good. But in case if you have any other use cases, maybe just distributing based on lag sorting is not sufficient, then we can use advanced algorithms like bin packing algorithm, where it will make sure that not just the partitions and sorting by the lag. It will make sure that the cumulative lag that one consumer gets is kind of balanced. If you compare with first case and second case scenario, right? In second case, we can see that the overall lag is kind of balanced. So that's the enhancement opportunity. But I think for our use case, we are stick with this sorting based algorithm, and it is working well for us. So these are the kind of a demo screenshot. If you can see here, so we kind of tested by producing 1 million messages across partition 0, 3, 6. The cumulative lag is around 1 million. So if we use the round robin assigner, so this is the behavior. Even if we restart any number of times, the assignment will be the same. So to distribute these high lag, we are using the lag based assigner. So we can clearly see that. So these partitions are distributed across the available consumer instances. So that, if this instance takes about 30 minutes, by using lag based assigner, we can kind of drain the lag within 10 minutes. So we can kind of drain the lag at 3x speed. So the next challenge, so to solve the express order problem, so we created the priority based partition assigner. So so to support Walmart's growing business, so we need to support the express orders. So from the producer side, what they decided is they have, in a topic, they have chosen a percentage of partitions to send the express order details, and the remaining partitions to send the normal order details. But from the consumer side, there is no way they can differentiate between the priority orders or priority partitions or the normal partitions, right? Because if you look at this consumer's internal buffer, we can see mix of express orders and the normal orders. So maybe the if you look at this green line, it represents express orders, and the gray lines represents the normal orders. So we can see that there is no priority among these orders. So consumers will treat all those as equal messages. So if you use the same situation, the high lag scenario, like I explained before, so it takes 30 minutes to process these messages. It is okay for normal orders to take 30 minutes, but in case of express orders, right, we have strict SLAs. So we need to deliver these express order to our downstream systems within 5-minute SLAs. So to solve that, we created this priority assigner. In that, what we do is user can select their priority partitions, so that using our assigner, we will only consume the data from those partitions until we meet the SLA. So once we drain all the lag from the priority partitions, then we start resuming from the other partitions. So this assigner we will only use during the incidents. It's like a standard SOP, so that we can kind of meet the business SLAs and and also support use cases like poison pill messages. In case if you have 100 partitions, one of the partition has a poison pill message, right, that continuously creates the rebalance issue. So in case if you want to avoid those scenarios also, we can just exclude that specific partition using this priority based assigner. So this is the pseudo code for priority based assigner. So we get the list of the partitions, and then based on user configurations, we know what are all the selected partitions and what are all the excluded partitions. So using this, we'll kind of combine and get the final partitions that we need to assign. And then on top of that, we'll apply the lag-based assigner. So this is the pseudo code. So currently we are using the selection algorithm here. So out of available partitions, we are only picking the priority partitions that are given by the user, and we are using those partitions to distribute among the available consumers. Now we are working on enhancing this one. So why to just pause consumption on the non-priority partitions? We can also use some kind of a weighted algorithm. So we divide available partitions into priority and non-priority buckets, and we'll give some kind of a weightage here. If you see here, so priority order 75%, non-priority 25%, right? So based on that, we will divide these available consumers to these two buckets. So since here priority is configured as 75%, so 75% out of 4 is 3. So we are using 3 consumer instances to drain lag from the priority partitions. So similarly, we are using only 1 consumer to drain from non-priority partitions. So this is, we are still improving our assigner. So this is a demo snapshot. So if you look at here, we have lag on 3 partitions. So partition 0, partition 3, and partition 6. But we wanted to only process the messages from partition 6. So if you see here, we are using the priority assigner, and only the actual consumer instance is connected to this partition, and it is committing the offset. So while we are not consuming any messages on the other partitions. So this is the use case of priority assigner. So in our messaging proxy service, we are using the combination of priority and lag-based assigners. So in MPS, we support 2 modes, the normal mode and the quality of service mode. So as part of that assignment logic, we'll see if the user is selected the QoS mode. If user selected, then we will take their priority buckets and all. Based on that, we'll select the final partitions. On top of that, we'll apply the lag-based assigner. And if a user is not selected the QoS mode, then we will use all the partitions. And on top of that, we are using the lag-based assigner. So lag-based assigner is working well for us, no issues and no partition skewness. And so we have in our code, we have the strict configuration validations, and also we have very strict timeouts. Like, if lag calculation or, fetching the offset takes more than couple of seconds, we will stop and we'll fall back on the default assigners. So that's the flow. So yeah, using these assigners, we were able to solve partition level priority, but still we have some use cases to solve message level priority or quality of service and message scheduling. So these are not natively supported in Kafka. So we are working on improving our services. Yeah, thank you. Happy to answer if you have any questions.
Wait, maybe there's some questions. Any questions in the room? So when you have the priority assigner in operation, what's the trigger to go back to the assigner that covers all the partitions, right? Because you're only covering 3 of those. At some point, you need to be able to go back and do a partition reassignment.
That's a great question. So that's why I said we will use this as one of the standard operating protocol. If you see any incident, so the manually or using the automated flows, we'll enable the priority assigner by only selecting specific partitions. Once we know that we drain the lag, we made the SLS, then we'll select all. So it's more like a manual process. Even if it is automated, but like, yeah, we need to check the lag, make sure that lag on this priority partitions is drained, then we will select all the partitions. Thank you.
Any more questions?
There's a question online. Why are rebalances the responsibility of application teams? When a consumer group attaches to a Kafka topic, isn't it the responsibility of the group coordinator to assign partitions to consumers, even if the consumer group resizes itself? Is this related to the version of Kafka in use? If I recall, group coordinators were introduced in 0.9.
Sorry, could you repeat the question?
Why are rebalances the responsibility of application teams? Is the primary question.
So application team's responsibility, we are not. Yeah, maybe if you want to take it.
Yeah, earlier when application teams were using the Kafka clients directly, so they were getting into these rebalance loops by adding more capacity. Whenever they scale out, they scale in, rebalances will happen because now you are changing the group membership. You have more members there. So that's what we flipped when we got a messaging proxy in the middle. So now we are working with a stable group that rarely changes, and your applications can scale in and scale out independently. And that's exactly what we solved, because the group membership is staying stable, and Kafka benefits from a stable consumer group more.
So to continue, to extend Bali's answer, so if you look at this example, right? So the default consumer assignment is not working for this use case. So as I mentioned, right? So it takes around 30 minutes to drain the lag, but user want to drain these messages quickly. So they don't have any control over this behavior. So we are kind of utilizing the same the Kafka provided mechanism, but we are extended the logic to distribute these assignments.
Yeah.
Go ahead.
How does consumer offset work here with messaging proxy in place?
Okay, so that's a good question. So you are talking about how do we commit back, right?
Yeah.
Okay, so here, as Bali mentioned, we separated the reader and the writer threads. So we read independently, we write independently. So on the writer side, we have a HTTP client. So that whenever it get the success responses, right, it will keep it in a queue. Just consider it will keep it in its buffer. And once it know that it committed it got the successful response to a series of offsets, right, then it will just commit to the end of that series. So we call it as an optimistic commit. So even though there are some messages processed by the end user, we might keep them as uncommitted until all the previous messages are committed.
One more question.
Hi, my question is also around the proxy. Since the proxy is this REST push-based method, but people were using Kafka clients before, that seems like a pretty big shift for the applications.
Right.
I'm wondering what tools and techniques you use to drive adoption of this proxy when it seems like it would have been a fair amount of work for applications to make the switch.
Yeah, Bali, do you want to take it or should?
You can take it. He was part of that.
Yeah. So luckily what happened is all these services, when they are integrated, like they are all small microservices. They're not just the Kafka consumers. They're all REST-based applications in general, but they have a Spring Kafka installed and pulling the messages. Luckily, when we said that, hey, you don't need to worry about polling and you don't need to worry about these rebalances issues and scaling problems, all they have to do is in their code, disable, like remove all the Kafka client dependencies and expose those APIs that process that particular messages to MPS service. In the MPS, we don't have any configuration where we are reading from, which endpoint we need to send. So it became a bit more easier than we thought. Initially, that was our concern was, but luckily everything was a Spring Boot. Walmart is a Java Spring Boot shop. So that kind of helped too.
All right. Thank you very much, Walmart. Next group is ClickHouse. By the way, if anybody online has more questions, put them into Q&A, and you guys can check it and answer online. So quick introduction. Sai here is a director at ClickHouse, where he leads the Postgres efforts. Prior to ClickHouse, he was a CEO, a co-founder of PeerDB, a database replication company, which was acquired by ClickHouse. Before that, he was a leader on the Microsoft Postgres team and an early engineer in Citus Data. Please go ahead.
Hello, can you hear me? Awesome. Great to be here. So I'll be talking about like operating Postgres change data capture at massive scale. Before I get started, I'd love to like introduce what ClickHouse is. So how many of you here have heard or like know of ClickHouse? I'm glad like more than half the room know about ClickHouse, but I'll still give like a high level summary. So ClickHouse is an open source, column oriented, distributed analytical database. It started as a project in 2009, went to production in 2012, and was supporting the second largest web analytics platform in the world. It was open sourced in 2016, and since then has been adopted by like thousands of companies, including companies like Netflix, Instacart, Meta, and many, many more. In 2021, ClickHouse Inc., the company behind ClickHouse, was formed with the goal of making it very seamless for customers to deploy and manage ClickHouse in the cloud. Second, ClickHouse is a column-oriented database with many specialized features focused on blazing fast analytics. Third, it is a distributed database. It is available with both sharding in the open source and separation of storage and compute architectures in the cloud. And it is available with like both multi-master as well as like cross-region for reliability. Last but not the least, it is an OLAP database. So like the laser focus is analytics, supporting aggregations, real-time visualizations on massive data sets. So with that, let me introduce myself in my words. So I'm Sai, and I lead like all the Postgres efforts in ClickHouse. So recently, what ClickHouse did is it is expanding to the OLTP transactional world, and we announced the native Postgres service, which is currently in private preview just like a week ago. And the idea with that is like it is deeply integrated with ClickHouse, providing a unified stack for transactions and analytics. So I lead that effort. Prior to that, like I was the co-founder and CEO at a database replication company called PeerDB. And what PeerDB did was it was a data replication company with laser focus on Postgres. So we made it very easy to replicate data from Postgres to external data stores, and ClickHouse was one of them, which is why ClickHouse acquired like PeerDB around 2 years ago. And the goal of that acquisition was to make it like very easy for customers to replicate data, sync data from Postgres to ClickHouse, and offload analytics. Prior to PeerDB, I was working at Microsoft in the Azure Postgres team, and prior to that, I was an early employee at Citus Data, which is a distributed Postgres database, open source Postgres database, which was acquired by Microsoft. So my life, like in the past 10 years, has been mostly around databases, open source, and specifically Postgres and ClickHouse. So before I get started, I would love to, give a quick primer of what Postgres change data capture is, right? Like, and I'll call that as like Postgres CDC, because I think that will make my life easier. So Postgres CDC represents a logical stream of changes as they happen in Postgres that external clients can infer and get a consistent snapshot of Postgres continuously. These changes are typically commands like inserts, updates, deletes, schema changes, which are like DDL commands, right? And external clients can consume them and like build the state of Postgres. Now, Postgres CDC has a bunch of real world use cases, right? For example, you replicate data from Postgres to like, databases like ClickHouse for like blazing fast real-time analytics, stream data from Postgres using Postgres CDC to Kafka for real-time alerting use cases. Apart from that, like you can also do homogeneous migrations where suppose you have Postgres databases in the self-hosted and you want to like get them to the cloud, you can use Postgres CDC for online like no downtime migrations. You can use Postgres CDC even for like online upgrades, right? Like if you have like you want to upgrade from Postgres 17 to 18, you can use Postgres CDC there as well. So with that, I want to introduce you folks to a couple of Postgres specific concepts related to Postgres CDC, and because they are important as prerequisites for this talk. First is something called as logical decoding. It is the technical mechanism behind Postgres CDC. It helps Postgres transform Postgres transaction log, which is nothing but the write-ahead log or the wall, into a stream of meaningful changes that external systems can understand. That is logical decoding. Next is logical replication slot, and this is the building block of logical decoding. Logical replication slot captures changes happening in Postgres through the write-ahead log and enables streaming of the write-ahead log in a logical, understandable format. Under the covers, it basically keeps track of wall that is already consumed and wall that is yet to be consumed. So at a high level, you can think of the logical replication slot as a data structure that keeps track of wall in an understandable format. Logical decoding is also tightly coupled with the Postgres process. This is unlike other like databases like MySQL, right? So consuming changes from the write-ahead log requires an active database connection, and Postgres retains the write-ahead log until those changes are actively acknowledged by the client. So if a replication slot isn't like actively consumed, the write-ahead log can start piling up, eat up disk space, and eventually crash the database. So TLDR, Postgres change data capture is fragile and needs to be handled with care. That's the reason I think we started a company and sold it to ClickHouse. But so that is one important thing to keep in mind, that it's a hard problem because of all these caveats. So here is a pseudocode that captures, Postgres logical decoding in action. So you have this is a Python client which is reading Postgres. You have the first like box which shows the start replication command, which reads the logical replication slot, right? And then the second box actually shows the client sending an acknowledgement to Postgres saying that, hey, I've read until this LSN, so you can flush the rest of the like wall which is behind this. So this is an example of that. Now that like we understood what is Postgres CDC, some technical concepts like logical decoding and logical replication slots, let's double click on why ClickHouse uses Postgres CDC at scale. Why is it important for us in first place? So basically it's coming from customers. So thousands of our customers like come from the Postgres world. They start with Postgres powering both like transactional and analytical workloads. And after, few months, as their application grows, they realize that Postgres is not sufficient for analytics. Their databases get slow, which is when they adopt ClickHouse, right? And one of the common reference architectures that we see is customers sync data in Postgres in real time to ClickHouse, make all the transactions in Postgres analytics ready, and power their like real-time analytics using ClickHouse. So this is the reason, like, this is one reference architecture that like a lot of our customers follow. Now, to make that easy in our like cloud platform, we introduced something called as ClickPipes. ClickPipes is the native managed ingestion service, which makes it very easy to ingest data from like various sources, like Postgres, like database sources like database CDC, streaming sources like Kafka, Red Panda, like Warp Stream. You have object storage sources like S3, like GCS, right? Like Azure Blob Storage. So all of that, like it supports. And what we have, and obviously like Postgres, as we are talking about Postgres, it's one of our largest sources. And here is a quick example of the product in action, because I think it'll be easy to tie all the dots together. So what happens is, the customer can enter all the Postgres credentials. Then within a few clicks, they can start selecting the tables that they want to sync, right? And then within a few clicks, the data is like replicated. Now this does two things. First is it does an initial snapshot of data. So you have a Postgres database with like 10 terabyte data that is like, replicated to ClickHouse, made analytics ready. And then the data that is like continuously getting into Postgres, that is also like synced in real time to ClickHouse. Now under the covers, it uses logical decoding, logical replication slots, all of that is abstracted away from the user. So here is the scale that we are talking about. So we launched the Postgres CDC connector in GA around like now 8-9 months ago, last May. And now it supports like over 500 customers. A lot of them are enterprises. Per month, we move around like 250 terabytes of data from like Postgres to ClickHouse. Last month, like that accounted to around like 300 billion plus rows. The total databases that like ClickPipes Postgres CDC handles is over 1,000 databases, and these are Postgres databases that are either self-hosted or in the cloud, like AWS, like or GCP, whichever like Postgres managed service. And then last but not the least, like the scale we operate is like this product is built to handle large Postgres databases, even at the scale of like 60 terabytes. That's one of our like largest like database. Now here is an example which shows like, a bunch of customers like Wuling, like Automate, Ashby, who use like the product. So one important thing I'd like to call out is the Postgres CDC in ClickPipes is built on an open source like tool, which is PeerDB. You can think of PeerDB very similar to Debezium, because I think you'll relate that more because like it's a well-known product in like, the Kafka world, right? It's very similar to Debezium, but laser focused on Postgres, right? Like, so we have like hundreds of optimizations in place for getting the Postgres CDC problem done really well, right? So Postgres CDC in ClickPipes is powered by PeerDB, except the UI, all the internal components are powered by this open source technology. So now that like, I talked about why Postgres CDC is important for ClickHouse, what is the scale that we operate, let me double click on what is the architecture that we follow that has helped us scale. So the architecture has a bunch of components, as you're seeing. So you have the user interacts to ClickPipes, right, through the UI or the API, right? And then they pass the request on, okay, this is my Postgres database, this is my ClickHouse service, and I want to like start like syncing tables from like Postgres to ClickHouse. The ClickPipes UI passes a gRPC request to the Flow API, right? And the Flow API forwards that to Temporal, which is our like workflow orchestration tool. We are big fans of Temporal, one of the super users, I'd say, and I can talk about that like offline. Then you have like two components, which is the snapshot worker and flow worker, right? If you remember, I said that Postgres CDC has two important steps. First is what we call as the initial load, where we get the initial copy of data, right? Existing copy of data in Postgres and put it to ClickHouse. And the second step is incremental sync, where like as changes happen in Postgres, we consume the write-ahead log and keep it in sync with ClickHouse. So those are the two steps. Now, snapshot worker is very critical in handling the first step, which is initial load. What it does is it holds a persistent connection, a snapshot connection to the Postgres database. The flow worker then, which is a separate component, uses that snapshot connection and does a consistent like snapshot of the data to ClickHouse, copies that data to ClickHouse. So this is very important to like, maintain consistency, right? Once the initial snapshot is done, the flow worker again, right, reads the wall, the write-ahead log, right? And then streams data to ClickHouse. Now, basically, if you look at it, the flow worker is a very resource intensive component, right? Because that's what actually is doing the data movement, right? And internally, we have like a bunch of optimizations to like, make the data movement as efficient as possible. For example, we, parallelize like tables wherever possible, parallelize the data movement wherever possible. For example, in the initial load, like we partition super large tables, logically partition them and like, shove it to ClickHouse. I'll talk more about that like soon. So parallelism wherever like possible, that is one. Next, like we use the right data format. So like we compress the data to Avro followed by ZSTD and like, replicate data to ClickHouse. Number 3, we also use S3 and GCS, which are our internal stages where like we consume data from Postgres, put it to S3. Then there is an asynchronous job, which reads from like S3 and then like puts it to ClickHouse. Now I'll talk about like why this decoupling of pushing to S3 and pulling from S3 is like important. So I'll talk about that in my future slides. So if you look at the architecture, right, each and every component of the architecture is stateless and horizontally scalable, right? So everything is like, fully scalable. The only place where we keep the state is something called as the catalog, which is here, right? And then that's a PostgreSQL database which stores like state, and we keep granular states. I'll go to that like next. And what we do is like, for every customer that like provisions a ClickPipe, this entire setup is like provision, and we use Kubernetes for all the, deployment under the cover. So I'll double click on that as well very, very soon. So now what we'll do is like, we'll look at the state machine, right? Like, so Postgres CDC is a complex problem, and these are all the different states that we have within like ClickPipes. So the first is what we call as the setup flow. What this does is it basically, sets up the replication job. It, does the schema translation, gets the tables from Postgres, creates them on ClickHouse with the right column types as native as possible. So it basically sets up the entire job. So that's the job of the setup flow. Then you have something called as the snapshot flow. So snapshot flow is, and the reason I keep using flow is because temporal has this concept called workflows, which are like basically states. That's the reason I keep saying flows. But coming back to the snapshot flow is responsible for the initial load of data, right? Copying the existing data from Postgres to ClickHouse. It has like, 2 substates, if you see. One is like the, snapshot transaction, right? Which holds the persistent connection to snapshot connection to, Postgres. And then you have the partitioned initial load, which basically partitions these large tables logically, and then, parallelly streams them to ClickHouse. And this is a loop, if you're seeing, right? Like, so we keep, like for every iteration, we store what partitions are finished and what partition needs to be done. I'll tell you the benefit of this, like, very, very soon. So now the initial load is done. Then the next state, which is CDC, right? So this is the continuous replication, which actually, consumes the write ahead log, like converts it to the right, like, Avro, blah, 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 puts it to S3, and then like puts it to like, a ClickHouse. The CDC like running state has 2 substates. One is the sync loop and the normalize loop. Sync loop, both of them are decoupled and asynchronous. So the sync loop continuously reads data from Postgres, puts it to S3, and then the normalized loop basically reads from S3 and then like, pushes it to ClickHouse. So if you look at it, like there are various components, various states. The first question you might get is like, is this too complex, right? Like, or is this like modular? I think we feel that it is modular and absolutely necessary for like enterprise grade and reliable CDC, right? So there are like, I mean, you could do stuff in a single binary, but like, this is important, like where you keep these states, keep it modular, and let's talk about those like benefits. First is the architecture lends itself really well for like, infrastructural isolation, right? Failures or scaling events in one component do not cascade to others. And this is critical for CDC because like it's full of failures, right? Like it's like this can fail, that can fail, S3 can go down, whatever. Like there are hundreds of like failure modes, and that infrastructure isolation is very, very helpful. I'll give you a specific example where this is very helpful. For example, in our like, here we have the snapshot worker and flow worker separated out, right? For whatever reason, the flow worker fails. It can happen, right? Like, for data format reasons or like, and out of memory, whatever, right? Like, and we have retry loops. It doesn't kill the snapshot connection because we have snapshot worker which is fully isolated, right? So we need not start from first. We can continue from where it left off, right? So it gives you that benefit of not like, restarting again. Second, it is the entire architecture is independently scalable, right? So each component that you are seeing can scale independently. And you can allocate resources, saying that for my flow worker, which is like, very resource intensive, I'll give, more resources. For my UI, I'll give less. So you can like, optimize your resources as needed. Third, idempotent retriable state transitions. This is very, very important. So each state is independently retriable, avoiding global restarts, right? So one advantage is like, for example, even the initial load, like we partition tables, right? So like if, for example, one partition fails, we don't need to start this entire 10 terabyte load again. We can just continue from where it left off, right? So basically, like there are so many states here, if you see, and capturing them like really helps in making it as efficient as possible. Next, we are decoupling workflows where needed, right? So decoupling Postgres to S3 and S3 to ClickHouse is very critical, because if ClickHouse for whatever reason goes down, we don't want like, the system to get choked and not consume the write ahead log, which can basically like screw up Postgres, right? Like, so it's very important that like both of these are like decoupled and we chew the slot like as efficiently as possible. Then you have like end-to-end observability via temporal. So this is one big benefit, right? Like temporal has some learning curve for engineers to ramp up, but like the benefit is you get like observability out of the box, right? So you get full visibility into your like state machine from workflows, like inputs, outputs, failures, traces, all of that out of the box. And we have seen that like very handy when there are like on-call, like, outages. The recent US East 1 outage, right, which happened a few months ago, temporal did really help at that time. Then finally, this architecture is a Kubernetes native architecture, because each of these are like components, and like Kubernetes has made our life very easy with respect to like, primitives, simplifying the deployment, like scaling and operational side of things. So with that, like now we talked about what are the benefits of this architecture, like many states, many components, right? Let's double click on a few decisions that I wanted to highlight that mattered a lot in like helping scale. And by the way, like we manage all of this with like a 3 to 4 member team. So like it has indeed worked. So now, let's talk about like, the first trade-off, right? Like this is why we even started the company, and that was our unique insight when we started PagerDuty, was like ETL and data movement should be like data store centric. So like we followed the philosophy of like building this entire product purpose built for Postgres. So any connector in ClickPipes, we do that, right? And a few examples. First is we have this feature called parallel snapshotting. I talked about it. This has the capability of replicating a single large table with parallel threads, right? So what we do is like Postgres has this concept of like CTIDs, which are nothing but tuple identifiers. So they are direct, pointers to a row on disk, right? So what we do is we logically partition that table, and then we use the state machine with temporal to parallelly stream that to like, ClickHouse. And the benefit is kind of like incredible. Like you can actually move terabytes of data in few hours versus days, basically. So TLDR, if you have a 30 terabyte like table and throw it to ClickPipes, you would probably finish like in few hours, versus like you try this on Debezium, it would take like, probably a week, basically. So that is the benefit that customers get. The second is like we have like, this always consume the replication slot. So this is in the philosophy of the product, right? Like, because finally we are dealing with OLTP databases, which are like the heart of the business, and we have to de-risk like load like as much as possible and keep them reliable. And one very important thing is like we need to consume the replication slot all the time. The third is like we also provide like a lot of Postgres native monitoring and observability, right? Finally, these are like, systems that run at like large scale, and without observability, it won't make sense. So like we provide like, replication slot size, like lag, number of connections, activity on Postgres, a bunch of like metrics that customers can like actually, use. The second like decision that has like helped a lot is obsessing over UX, right? Like finally we are like serving like thousands of companies. Like, so every like since day one as well, and also like daily we iterate a lot on like user experience, so that like we make it as scalable as possible for customers. A few things are like, say, validation while pipe creation, right? So when someone is creating a pipe, right, like there are thousands of edge cases, like, Postgres is not reachable, ClickHouse is like, service is idle, like my table does not have a primary key, like, there are thousands of these edge cases. And then like we have like, guardrails for each of them where customers actually look at, okay, this is the issue, and they have like clear like a link to the docs, right, like where they can go and like fix the issue. So what I have here is like, a sample of the code. These are like just switch and if statements, nothing complex here, but it captures all these like, edge cases. The second is, okay, now I kicked off the pipe, my replication job is running, but there could be failures, once the replication job is running as well, right? Like say my Postgres is down, now, what do I do? So for that, like we launched like this feature called issue specific notifications. These are nothing but alerts, but these are very specific to the issue that the customer is running into, right? For example, this shows like replication slot growth, which is one of the most common issues that we see, where like, we tell the customer that, hey, you're running into a replication slot growth, which could be normal. You're having a long running transaction, which could be normal. But then like, here is docs on like, going and checking why this is happening, right? Because it's very, very important. So like this is one. Next is we provide like, incredible nuts and bolts, right? Like, I mean, a lot of granular configurability. There are advanced settings where, customers can choose specific columns, specific like, table engines. They can tune like ClickHouse. They can, specify parallelism. And there are like requests from customers that I want to resync this particular table, like remove this particular table. Like it's very workload specific, right? Like, and Postgres has hundreds of like, tables most of the times. So we give like granular configurability as much as possible, so that customers can like, fix it and like, manage the pipe themselves. And like, this is a common problem. And like, I think we just boiled some part of the ocean, the entire ocean is left. But like granular like configurability is also very important. Then now that like, we have talked about like a few decisions and philosophies that have helped us scale, I'll talk about, what are the big gaps and like what's next. First is, Postgres CDC itself like does not support comprehensive schema changes in a Postgres CDC. For example, alter column default is like not there, right? So that is something that like we would like to work on. And now that like we also launched the native Postgres service, we do want to actively contribute to Postgres. So that is something that we will do. We have a Postgres core team that like we're actively building out. Then we have like sub-second replication is not yet possible, right? Like because of, various reasons, like in ClickHouse, we're doing batch inserts, right? Like we are like using S3, right? Like, so, and we have seen like latencies up to 5-10 seconds. ClickHouse is already like very, very good. Like if you were to do this with other warehouse, it would be like few tens of minutes or something. But we want to, focus on sub-second latency. For this, ClickHouse released a bunch of features like, async inserts and stuff like that. So we will be working on that. Next is replication slot growth remains a common operational concern. And this kind of ties into like, caveats around Postgres, where a single replication slot is like consuming it is single threaded, right? Like, and then, there are challenges around high throughput workloads and large transactions. One feature that we want to add in our like, CDC experience is logical replication v2. So this is Postgres protocol, which actually lets you consume in-process transactions, right? Now that's a challenging thing to implement because like, we need to take care of the transactional semantics, right? Like CDC, like the logical decoding doesn't, but we want to like, do that. And we have seen this drastically help throughput, like flush slots much, much better. And then, finally, logical, this is, again, related to Postgres, like logical decoding is single threaded. So a single slot can be read only via a single thread. I've seen throughputs about around like 30 to 50K transactions per second reliably, basically, right? Like, so, which is mostly fine, but like, as specifically with AI, like the amount of like, the scale is only increasing. So like, I think it will get important where like, it becomes multi-threaded. Last but not the least, we see like a lot of, differences in like data modeling between Postgres and ClickHouse. This is a gap that we have to bridge because we are seeing a lot of Postgres users. We recently added like, lightweight updates, which will let you update data within like few milliseconds. So there will be active focus on, how do we make the data model very similar, right? Like, I mean, normalize schemas, like joins and all of that. Like we are, focusing on that. Yeah, with that, like, I mean, just want to like talk about, we recently launched the Postgres managed service. We'll be like, really like this is a strategic initiative, and we'll be doubling down on Postgres and making the CDC experience even more native. And the idea is like to provide like a unified data stack for like transactions and analytics, because this is what we are seeing across our customers. And if only you're interested, you should sign up, and happy to give you an access where you can see best of both worlds: Postgres for transactions, ClickHouse for analytics. And yeah, with that, thank you so much for inviting me.
So first of all, thank you for the presentation, very insightful. So the question is, in my experience, this write-ahead log where all data is written, like, and even uncommitted transaction elements are committed, it may impact latency when you restart your connector. Like if you're reading in between, you have to fall back and start reading over, right? And you said like you aim towards like some low latencies. Have you, like, besides this like V2 replication protocol, do you have any other workarounds to mitigate that?
Fantastic. I think one of the major changes that we did in the product is we never give up reading the replication slot. So like in first place, like you see the replication slot running for like months, like that action, like activity is like always like, I mean, the connection is always active for the same reason that you said. If we disconnect, it will start from the restarted lesson, not the confirm flusher lesson. So it starts from the start of the slot, right? So we already have mechanisms where we never give up reading the slot. Now in a logical replication, V2, I mean, will help overall. But finally, like, a connection restarting, I mean, starting from the restarted lesson, that's very core to Postgres, right? Like, because it needs to build a state. So it does not have like, metadata tables, blah, blah, blah. It's more complex than that. It's an OLTP database, right? Like, so it's more complex than that. But that is something that we will aim to contribute in the future, where like restarting the connection, it actually picks up from where it left off, then starting from the slot. That's a foundational issue of Postgres. So yeah. Great question.
Thank you.
Any more questions? Anything online? No? One more question.
So basic question, how do you handle race condition if like the snapshot worker is still working and there is a new update to Postgres DB? How does the CDC take care?
Exactly. So the snapshot the snapshot worker, I mean, the initial load and CDC are incremental and sequential. So like while the initial load, like the changes are in the replication slot, basically. And the good thing is like initial load is already very, very fast. So the replication slot doesn't grow, right? So after the initial load finishes, then only we read the replication slot from Postgres. One feature that we are working on is like, while the initial load, like, I mean, is happening, we flush the replication slot to S3, right? Like, and then like, read from S3 later. But TLDR, the reason consistency like happens here is because like we keep it sequential. We don't like parallelize and we push it to like, we don't do it that way. So, yeah. Exactly. Yeah. We do the initial load and then the CDC. Awesome.
How is this replic lag? How do you measure that? And especially if there are any failures, how do you maintain or like reconciliate the lag metrics?
That's a very good question. So that's a challenge. So Postgres does not like have a mechanism where it gives you like the replication lag in seconds. So you have replication lag in, like, if you measure the size of the slot, that is replication lag, right? So that be exposed to the customer. For mechanisms where like, to measure the replication slot in seconds, the only way is like you need to have a table that is replicated in both sides. So you have like a timestamp like table which you continuously update and then subtract, right? That's what customers do. But that is one way we are like thinking basically. So currently we don't provide the lag metric in seconds, but that's the only way as of now. So yeah.
All right. Thank you very much.
Awesome. Thank you.
Our next presenter is Wei Qing from LinkedIn. She's been working in big data computation frameworks since 2015. She's currently a software engineer on streaming infra team at LinkedIn. She's working on Flink, Samza, Kubernetes, and so on. Before that, she worked on Spark at Hortonworks. Wei Qing is an active member of the tech community and frequent conference speaker. She's presented at Spark Summit, HBaseCon, KubeCon, ApacheCon, Flink Forward, and Current. Please go ahead.
Hi, everyone. I'm Wei Qing. I'm software engineer at LinkedIn working on stream processing. Today, I'm excited to talk about how we are powering stateful join at scale with Flink SQL. My co-speaker, Pravish today, couldn't make it today. But I'm here. I will walk you through our journey and lessons we have learned along the way. By the way, how many people here know work on Flink before? Okay, most of them. So yeah, Flink is a streaming computation engine. So here is the agenda for today. First, I will start with the motivation, what's tracking, and why do we need to join. And then I will talk about the new architecture with Flink SQL and some typical use cases. And then I will give a deep dive on bottleneck, capacity planning, and reliability, and so on. So in the end, I will wrap up with challenges and learnings. So what's tracking? At LinkedIn, tracking is our data foundation that helps us to understand how feature performs and deliver values to our member. Then still, why do we need joins? So we have generic client event. So for deeper insights, developers need to join those client-side event with the backend server-side event to combine, and that a join will create enriched and combined information for advanced analytics. And here is the early version of our tracking join looks like. It used stand-up bin and Couchbase. So Couchbase will store the inputs for remote lookup. So Couchbase is act as the storage, and then stand-up will query it during the processing. So here is the tracking system scale looks like. This is per each job instance. The input QPS could be 200 to 300K QPS from the Kafka streams. And per job state, the state size could be 5 TB with 2 days retention. And for a latency requirement is strict. So you see the P95 need to under 20 seconds. And summarizing all, there are more than 400 output streams and cross more than thousands job instances. So with such scale, the old version, the old tracking system worked, but it hit pain point. So we need some of them here. First is high operational toil, because we need to manage 5 TB state size per instance in Couchbase. So the maintenance cost is expensive. And then there's Java API, so there's no SQL. So for example, we need to write more than 100 Java code, but instead, if we write in SQL, it's just 10 lines of code. And also the high infra cost. So because Couchbase is act as the remote lookup store, so there is a remote cost. And also standard jobs use more CPU and memory than Flink. And there are like Couchbase hardware, Couchbase operational cost. So it's a high cost. That's why we moved to Flink SQL. So Flink SQL at LinkedIn is managed platform. So if user on board to Flink SQL, then they don't need to they just need to focus on their basic logic. And the second we need to mention here is with Flink SQL, our customer can leverage the string and batch unified solution at LinkedIn. So I put a link here. So it's talking about how the string batch unification solution looks like at LinkedIn. Okay. So what does the major platform at LinkedIn looks like? So what we are offer? So our one of the core value here is we want our string job developers just focus on their business logic, write SQL, write UDF, and then leave all other aspects to the platform team. So user can just focus on authoring their app, test, deploy it, and then platform team will, for example, take care of the operation aspects to do configuration management, platform version upgrade, alerting, and so on, including the resource management, for example, auto-sizing. So let's take a look at state backend, how the state backend architecture looks like. So Flink keep state local for performance. So we put the job state, we leverage the RocksDB as our state backend, and then we put the local state on NVMe. So put the state local is not enough. For example, the job failed and the worker will move around. Then how to make sure that the job can resume the state and then restart. So, okay, so Flink will periodically to snapshot and backup the state to the remote store. So at LinkedIn, we use Embry. So Embry is our distributed blob store. So we put the state and backup there. So whenever the job failed, and the task manager will download the state from Embry and start from there. Okay, now we have already go through the high-level architecture. With the new architecture with the Flink SQL, how does the tracking neon line join looks like? So we can see it's much simpler. So everything will be inside Flink. So there is no Couchbase anymore. So the Flink will manage the state and the lifecycle clean up itself, because it will leverage the RocksDB backend to take care of it. So here in these slides is list out a typical join use case here. There are two main input stream, one from the client side, another one from the server side. And then each stream will go through some filtering, go through some fan out based on their business logic. And then we'll go to an interval join, typical is 2 days, and then combine those two strings information to output stream. So all those join be leveraged by a lot of business critical products at LinkedIn. For example, notification, search, jobs, and premium. Premium feature like the AI assistant draft. Hope everybody used it before. Okay, now we deep dive some error. First one is the bottleneck. So I understand what's the bottleneck of the pipelines running in the cluster is very critical. Otherwise, it will be black box to us. So we ran some performance tests and observed the task manager disk read and write I/O throttled at around 5K on SATA SSD. So we now understand the disk I/O became the bottleneck for the interval join task. So with awareness of this bottleneck, we can do resource estimation for the jobs. So how to do the resource estimation? We define 3 scenarios: happy path, catch up, happy path, and unhappy path. Unhappy path include the catch up and job recovery. So happy path means the job is running perfectly, it's running stable, so it's straightforward. But for catch up and job recovery, so it depends on the time, and also depends on the event volume. That means if you want your job recovery faster, or want your job catch up faster, that means you need more resources. So here, depend on each scenario, we build and we develop a formula. So I won't go through the formula here. They're all math. But the formula benefit here is we need to we should be able to answer one question: is how many task manager does the job really need? So yeah, those formula can help. So now let's assume we know how many task manager we need to for this particular job, and we know per TM resources. Then we can translate those numbers into how many nodes the job required based on the node profile. So now we can do a resource estimation at the job level. So we can leverage the same approach to do the capacity planning, the annual capacity planning at platform level. But as we know, we consider the maximum, the worst case, when we do estimation for each job. But if we do platform level estimation, for example, just naively to sum up those worst case estimation, that means we'll overkill the overall capacity planning. So that's why we need to balance some factor into platform capacity planning. The first one we list out here is the peak traffic adjustment. So instead of just sum up the worst case resource across the job, we can apply some average factor, for example, the 60%, to avoid provisioning for worst case across all pipelines. Yeah, so another one is the shared catch up. Similar to the previous one, not all the job will fail at the same time. Not all the job will catch up the lagging at the same time. So rather than just sum up the numbers across the job, we can for this one is just we find out we just find the max catch up across the job, and then use that to add to the happy path estimation. Okay, so here we can combine the balanced factors. We can calculate there may be 4 combinations. So in practice, you can choose, our customer can choose one of them just to fit their requirements the best. It could be peak only, a catch up buffer only, or both of them. Okay, so now we have already understand our the bottleneck for the job. So it's the disk I/O. So then we switch from the SATA SSD to NVMe SSD. We achieved 5 times higher QPS, and also result in 80% hardware cost saving, because we can use far less host for the tracking jobs. This slide is we trying to help our customer to help them onboard and test their use case, to boost their onboarding speed. So we build an end-to-end test framework. So this framework is to deploy a local Flink cluster and then determine the input Kafka topics from the job configurations, and then generate and render some test data for the test pipeline, and finally, and then validate on how to verify the correctness of the result. That will help a lot, actually. So because when the user trying to, after they ordering their SQL job, they just click a button, then we'll go through the end-to-end testing workflow. So let's talk about the reliability. So most of the SQL job, the Flink SQL job, so their input topic schema could evolve over time. For example, one common use case is the customer's input schema, they added a new nullable field into a complexity raw data structure. So from their perspective, the schema change is backward compatible. So, but in practice, the job could fail during the data store phase. So we have already resolved this to improve this, to support state schema evolution for raw data. We have already applied in our production. So now we are working with the open source to upstream it. Okay, another challenge about reliability is about the job tuning and the runtime stability. There are two issues happened just recursively happen. One is the inefficient job sizing. Another one is the how to debug. So for the sizing, we built a built-in job validator trying to catch up the issues or miss, for example, or like the configuration validation during the build time. And during the runtime, we also build auto-sizer. So auto-sizer based on the history metrics and to provision a better CPU and memory source for the job. And for the to improve the debugging experience, so we spend a lot of time to enhance the logging and observability. Also trying to allow our user to split the complex SQL into smaller one with previews. So for the error message, we also spend time there to clarify complex messages or cryptic error message for them to faster diagnostic their job failure. Okay, so we also, beyond the reliability, we also need to help our customer to operation, like not just for our customer, for ourselves as well. So we need to build tooling. So there are two, I call out two of them. One is the job redeployment start point. So this enable our customer to restart or redeploy the job from a choosing point in time. So they can just restart their job with any timestamp to redeploy the job. So the configuration could be at Kafka topic level, partition level, or job level. Another one is the capacity readiness. So when the job owner need to deploy their job, so we always have a capacity check to ensure the job can only be deployed when there is enough available resources. And we also implement a quota management to prevent resource contention across the pipelines. Okay, the final is a backfill automation. So we automated a backfill workflow and to avoid to help our user to backfill their job with minimum user input. So they can also leverage the stream batch unification solutions at LinkedIn for their data processing. So in the end, let's wrap up. The challenge we have been facing, first one is to debug and resolve complexity memory allocation issue, to debug the memory issue out of memory. And another one is the job tuning to ensure runtime stability. So it's hard to debug sometimes, especially for the high QBS and large state applications. And then is to manage another challenge is to manage large state application efficiently and to improve their checkpointing efficiency. The last one is our major milestone. So we achieved to migrate the old tracking system from Samza to Flink with zero downtime. So that's great. And learnings. We call out 4 of them. They look like very simple, but actually very useful. The first one is to build end-to-end metrics and efficient logging to make sure we have enough information to do the debugging and quickly identify RC issues. And before go to the production, we start here to do enough benchmarking to understand what's your platform limits. The third is to understand the recovery and catch up time, and also those balancing factors when you do resource estimation, when you do the annual capacity planning. Next one. So tooling, robust tooling is not optional, it is a must to have. So it's the key to improve triage capability. So with all of that, thank you for joining the talk. Thank you.
Any questions?
It looks like you've done a lot of work to help define the capacity requirements for the application SQL jobs running inside Flink, right? Understanding how much task manager resources are required, understanding before the job gets even launched that there's enough capacity in the whole system. How did you build those heuristics, right? This is a how long a piece of string kind of question. Most of the applications I've seen, deployments I've seen, how complex a Flink SQL job is. Plenty of application developers can write a SQL job that will take down any cluster I can provision. And so how do you get to the point where your platform is more stable for your application developers?
Yeah. So fortunately for this tracking system, we can see we have more than thousands of jobs. Their logic is very similar. Their source could be different, but logic they do interval join, 2 days state rotation. So when we do the benchmark to understand the bottleneck, that bottleneck can apply to cross the job instance for the tracking system.
So the applications themselves are fairly homogeneous, so you can use the learnings from the first 37 that have been deployed to map out the requirements for the next 30.
Yeah, that's true.
Okay, thank you.
Yeah, we use those history data to do estimation for future workload.
Yeah, thank you for the talk. I have a question around Flink SQL. When you do the capacity planning, is it bundled into the cost-based optimizer, or it is kept separate from that and capacity planning first and then SQL running there?
Oh, sorry, can you say it again?
Is it bundled as a cost-based optimization step when you plan your capacity?
When
you input the Flink SQL. So do you do any cost-based optimizations, knowing the statistics of the stream, how much QPS it's coming?
Yeah, we need to do that. Yeah, the QPS and also the state size. So we need to understand the nature of the job, the workload, how much workload there, and how much state, and how much state could be per TM level. That kind of information we get.
Okay, so my question was like, all that information going into the cost-based optimizer for Flink, or is it being done as heuristically outside of that?
It's outside of that. It's outside of that. So it's a different tooling we built. Okay. Basically, it's outside. Okay. It's not internal.
That answers the question. Yeah. Thank you.
So as a application developer, if I write my own Flink job versus leveraging this platform to write this Flink job using the same SQL interface, was there anything that you do in addition to that as a developer? If I don't know Flink, is there any other optimization that you put in place from the platform side?
Yeah, from user perspective, the language requires SQL-like. So if you know how to write SQL, then you know how to write a Flink SQL job. So I see. So we're fully open source. We align with open source Flink SQL interface at all. We don't build any, for example, we don't add any sugar wrapper syntax at all. We don't do that because yeah, it's widely used. So it's a very I will say a lot of use for document in the open source. So sometimes we found that our customer prefer to search online, even like than the internal documents. Yeah. Thank you.
Any more questions? All right. Thank you very much, Wei-Ching.
Thank you, everyone. Thank you.
All right, guys. That concludes our meetup. Feel free to stay a little bit if you want. There may be some food left. Thank you everybody for coming, and we'll upload the recording. There's no questions. All right. Thank you.